Alright, hello and welcome back to my channel. And yeah, right now we are learning some BSP, and we've done 2 streams. This is the 3rd stream here, and what it is that BSP stands for binary space partitioning, and it's a way to kind of divide. It's like an optimization algorithm for dividing space into partitions to make it easier to locate where stuff is, or yeah, it can be used for rendering optimization and collision detection. It was used in Doom and Quake, I guess maybe most notably for optimization there. So, but apparently it's not a modern algorithm that is used anymore. So it is kind of, but it's still interesting to kind of learn a little bit of history and you know, kind of what the idea is, how it works, and there's some maths involved that I haven't really delved too deep into. I'm just copying basically some algorithms, or well, some calculations basically. But yeah, we have this little program here in Zig and Raylib, which well, right now it looks like this. It's kind of like a yeah, kind of like a very basic demo thing, 3D world that you can move around in, and we have these walls that are drawn based on if we can, like, if we're looking at them or not, or if they are facing us rather. So if we move upwards, you can see that the walls that are not facing us, that is the walls that are like on the other side of each of these kind of like rectangles or cubes things, cuboids, they are not actually drawn out. So that is one of the like optimizations that you get from this algorithm. That's very easy to get all the, you can filter out basically all the walls that are facing away from you. And what I was trying to do as well was to follow some kind of guide to implement this, and then try to use it for the rendering optimization, which we've basically done now. We have a balanced BSP tree. Well, as balanced as it gets when you try a bunch of different variations of the tree. We're not trying to algorithmically find a best tree. We're using like a random we're looking at a bunch of random trees, and then we're picking the best one basically. And then I think what we tried to do was to make some collision detection. Oh, by the way, this stream probably, I'm not sure exactly how much time I have, but probably not that much, so it's probably gonna be a very short stream. But I just thought that, hey, I had nothing else to do right now, so I thought I'd look at this a little bit more and pop in here and just explore a little bit more. So yeah, as I said, we did some well, I tried to do some collision detection. I've tried to do a little bit of research and try to like get this into my head, like how we can use the BSP tree to actually do something here. So maybe it would be cool if we could maybe visualize the BSP tree somehow. I mean, we could maybe do that. The thing, so I had this drawing that I made as well. Oh yeah, you can actually see it when I tab into it. So basically, Well, it's kind of trying me to understand how this algorithm works, and I should have sectioned this into different layers, but really, if we remove all this, I'm gonna try and make this into a separate layer here. So let's see. So basically all of that. Oh yeah, and here. This is, whoops. And this one. Okay. So if we remove that, we get this. Okay. So this is kind of the original, well, okay, plus this as well. So I'm gonna cut that, paste it into its own thing, okay. And I'm gonna paint this in and try to explain a little bit what I'm trying to figure out here. So basically, this is the level here. All right. Now you probably usually want to have a boundary around as well, but let's just focus on this for now. Okay. So what this is basically the cubes, or the kind of the cuboids here, or the rectangles. What you're looking at here is like a 2D map from top down. So you're looking at a top-down view of the map. So this is how, if you ever used like the Doom editor, Doom level editor, it would look something like this. Like it's actually just a 2D map that you draw these lines on. And when you draw a line, it usually got this little line out here. Each line here is a segment, what's called a segment. And basically it's just a line with a start and an end. So we have like start and end, let's say, or the other way around, depending on. So basically you start here and here, and then around the start point you can imagine a clockwise circle that goes in a clockwise direction, and that's why you're seeing this this thing here, because it like points in the clockwise direction. So that is how it determines which way this is pointing. And what this is basically just the direction of the wall. So each segment has a start point, an end point, and also a direction. But the direction is kind of, it's like implicit, because you can calculate it from the start and end position. But it means that it's the direction that it's facing. So if the player, excuse me, is standing over here, let me make a new layer for the player here. So that's the player. Okay. So that's the player. So if the player is standing over here, whoops, that means that we are like facing the wall. So that means we should see this wall. This wall should be rendered, right? But this wall over here is facing away from us. So that means it doesn't need to be rendered, because we don't see it, because it's like obscured by every other wall here. So that is that's the basic idea. And how to actually know which walls are facing us or not is efficiently stored in a BSP tree. So what we're doing is that we have all these segments. So we have 1, 2, 3, 4, 5, 6, 7, 8 segments in this level total. And we just start, and these segments are just they are just in a list, and so, or in an array. And so so what we do is we just pick the first one. So let's say this is the first one in the list, so we pick this one, and then we check, okay, we create a plane from that. So this is the algorithm. We create a plane like this, which cuts through basically all of space here. Okay, and the plane also has a direction, I believe. It has the same direction as the segment, so it has this direction like this. Oops, let me actually put this in another layer here. Okay, so this is the, so now this is the, this is that split, as it's called. It's a splitter. It's a splitter because it potentially could split other segments. But then the thing that we do here is that we go through each other segment. So we already did this segment. So that is the segment that's kind of bound to this splitter. And so we take every other segment and we divide those by if it's behind this segment or if it's in front of the segment. So all of these segments here are gonna be ending up in the, they are gonna end up in the list that is behind this segment. So this is the binary part as well, because this the whole space is now divided in two, where this space is the left part, left hand side, or the behind side, behind the arrow, and this part is the in the front. Okay, so all of these segments will be in the front and everything, or I mean in the back, and everything here is in the front. So given that you have this, you start at this root node, this root splitter segment in the tree, this will become the root node. And so if you go to the back side, you know that you're always going to be behind this root node. If you go to the front side, you know that you're always going to be in the front. Okay? And then you continue. So, well, yeah, so then we continue. So either you could, now it doesn't matter, you can do like the back and front side in parallel if you want. You can parallelize this because it doesn't matter, because they are kind of, they don't really affect each other. It's like now we're in two different parallel worlds, you can almost say. So let's start with this side. I think nothing here, nothing interesting, I think, is gonna happen here, because we're simply gonna, nothing is gonna split, is my is the idea here. So so this layer, let me actually create a new one for this as well. So now let's take this one for example. Now, since the world only like consists of kind of this this boundary here, let me actually just select this so we can, so that we can see this. That means that this splitter only reaches over here, because this doesn't exist in this world, you can say. So so here's a new splitter in this world, and now this is divided in two as well. So that's also the binary part here. So this becomes a new section which is actually empty, so there's nothing here. While this section here, so the front side is actually empty, and we know this in the data later because we assign that to null. And then the back, but the back side here actually has some children. So so then you know, we just continue here to pick the next one, which could happen just, it doesn't matter if it's vertical or horizontal, or it can be any angle actually, but let's just pick this one. So that's gonna get split like this, and then since it's facing this way, the segment actually is pointing this way now. Okay, and then this one doesn't have anything in front. It has one item here in the back, so that also ends up in its own thing here. Oops. So there we go. There's that one. Hello, hello, HP. I am welcome. I am going through like the BSP algorithm to kind of get more intuition on how it works a little bit, and also like explaining a little bit on how it works. So right now, well, now we've done this side, and we can continue on doing this side the same way. So it's just going to be the same way. And nothing really interesting is going to happen. There's not going to be any splits because we don't have any collisions on these lines right now. Because we started with this line, there's not going to be any collisions happening. So, well, I mean, when I say collisions, I don't mean like in-game collisions. I mean collisions regarding this, how the BSP tree is built. So if we go back a little bit, so that was the case where the tree was starting here. We split that, and then we continue with the back side here, and that splits these parts, right? Now, let's say we have this here, and we take the player, and we kind of move the... Whoa, wait. No, I want to move... There. I want to move the player. Actually, layer to... Oh, there's a thing there. I want to shrink this layer. There we go. Okay, so let's say we move this thing here. Aren't the fundamentals just splitting squares into a smaller, evenly spaced square within the same square? I think that is the that's the quad tree, or are you thinking about the quad tree algorithm? But because yeah, this is the binary space partitioning algorithm. So I mean, this particular example is for the first of all, this is like in 2D right now. There's a 3D version as well. You can have any number of dimensions, but this is the 2-dimensional version where we split the world into, you always split the whole world in two, and then you create smaller worlds that you also continue to split in two until you're done. And the thing you're basing it on are the actual level parts that exists in the world. Yeah, it's more, according to Wikipedia or whatever, it is like a generic version of the quad tree. But I'm trying to gather more intuition about it, and apparently it's not really like a modern algorithm used anymore. It was mainly used for things like Doom and Quake back in the day. I think it actually, if I remember, it was in Half-Life as well. I used to do some. Not modding stuff, but I think or was it Unreal or something like that? Anyway, it was like old FPS. It was used for optimization. Well, I'm not actually using it. I'm just trying to learn it because I asked on Discord for stuff to do on like a single stream, and this was one of the suggestions. So, but now this is the third stream that I'm kind of delving into it a little bit, because it is quite interesting learning about these kind of algorithms and stuff. because I want to learn more about game development. And although it's not like a modern algorithm, it's kind of cool to learn how these old school games used to do it as well. And you kind of learn a little bit tidbits of like maths and stuff underneath as well. But yeah, I'm just trying to gain some more intuition here to actually understand about how this kind of works. Let me actually put these in a group here. So now they are in a group, so I can disable them. So this is the original level, right? And then this is like the split of the first part here. This is like this part here. But what I'm trying to figure out here now is like when our player moves around, how we're trying to determine, what collision, how the collision system would work. So we kind of last time we looked a little bit on how Quake works, which of course it's a more advanced model because it's using a 3D map, and but what was quite interesting there is that the BSP trees are these pre-built trees that you can store in data. So you kind of optimize the maps by building this data tree from a static kind of map that gives you the data that you need to do all this stuff. And hey Blue, what's up, welcome back. And it was using that to also help with collision detection. And so the way they kind of did it is that somehow, if you have a point, you can kind of see, you can cast a ray to see if you're colliding with something. It's also a way to kind of say if you're shooting at something, you do a ray trace to see where you're like colliding first, right? And so, but a player is like larger than a point, right? So it's like a player is has some kind of volume. A point is just a point in space. So how do we check if the whole player goes through the wall? How they did it was they basically just expanded or extruded the map so that these boxes were like larger than normal. And then they made a BSP tree of that and saw that, okay, well, if we collide with this box, if we collide with this box now, okay, then we know that the player actually collided with the inner wall. So that was that was really clever how they did that. But I'm just trying to figure out the algorithm for checking if a line intersects with this, because the BSP can be used to do that as well. Oh, your PC is fried. What happened? Sorry to hear that. Don't throw water on it or anything. Anyway, so let's say we are here and we're casting a ray here. Obviously, it should collide with this wall. Let's see. And let's use another color here. So we're shooting a ray here. Okay. To see if we're gonna collide with this wall. And since this is the root node, we actually could just check against the root node and we see that we actually do collide. So that should be it, right? Then we found it. But what if we move this here? So let's say we move you. Hang on. we move you, whoops, we move you like over here, let's say. Okay. Now remember, it's only this part that's solid here, so it's not like the entire line over here. But as we can see here, this splitter like reaches, this root node reaches the whole thing. But we can see that only, yeah, it's going through this line to the back side here. So I guess we need to check. We see that it goes through here, and we need to check if, I guess, all the things in the back here. I mean, yeah, it's a root, it's a tree, a binary tree, so the back child of this is here. So I guess we need to check that as well, right? I don't know. This is where I'm getting a little bit confused on how to actually do this, because it's like I'm trying to see where we watched like a video on how the Quake video. Let's see if we can find this again. Yeah, here it is. Because it explained this maybe a little bit. Tree. Okay. It's just like, how do we find
and a line segment that lies within the node? The function returns a boolean saying whether the line segment intersects a solid. If so, the first point of intersection is also returned. The line...
I'll question, why Zig? Why not? Man, I get this question so many times. I find it to be a fascinating language, and it's like I would, you know, if you're gonna compare it, let's say, to C or C++, I think that it is, well, I mean, to me, it is easier to use. To me it makes more sense. I mean, I haven't used C++, like modern C++, for a long time, well, or ever, I guess. I mean, it becomes more modern as we speak. When I was young, I learned C++, but that was like a long time ago, and I tried to go back to it a couple of years ago, but I felt like, man, this is like moving through some kind of, you know, honey liquid or something. It didn't feel good at all, and I was looking for like a low-level programming language, and I found Zig, and it works extremely well. So, you know, that's it. That's that basically. And it also, I mean, it does interface with C very well. So you can use, like, if you really want to use like a C library, you can import a C library straight out of the box, and use that if you want to use something like, for example, Raylib, that I'm actually using to create this demonstration, or this thing here. So yeah, that's basically it. Hope that answered your question. But yeah, have you used Zig yourself? Or what other languages have you used? Because it's like, it depends. Like, sometimes people come from a C++ background who ask, like, if you why Zig. Sometimes people come from, you know, I don't know, Rust or Odin or something else. I was about to ask what graphics library you're using, but I'll guess to answer. Yeah. Raylib is like extremely easy to use. Primarily C. Okay. Yeah. I mean, I might actually do C, like a very small project in C, just to compare the two. I mean, I'm not a total noob. You know, I've been programming for a long time. I mean, in C. I mean, I haven't programmed in a long time in C, but I have been programming a long time in like all kinds of languages. But it would be interesting to just make some, you know, some small-ish Raylib project in C, just to, you know, explore that a little bit. But I doubt that I would leave Zig for C at any point at any point in time. Hello, said who? Welcome back. Hello, Ian. Welcome. I was dreaming BSP realized solution buffer got everything. Yeah, that's usually how it goes. Alright, I'm trying to figure out how to do the ray trace, like how to, well, we can check if lines intersect, but I want to see, like, how do we use the BSP to optimize it?
It's defined as a start point P1 and an end point P2. The point of intersection is the nearest point to P1 that is both on the line segment.
Isn't OpenGL basically obsolete? I don't know. I don't think so. It's probably used a lot still. Like, I'm not a game developer, you know, by trade, so I don't really know. I can't really say, but I would assume since it has been so huge, it's probably still used. In a sense, making something using it now. Yeah, I don't know. Are you talking about using like an more abstract, like abstracted library, or using something like Vulkan instead? Or C is easier to write than Zig for me. Yeah.
Wait.
All right.
We can immediately.
Well, it is for me as well because I'm not used to C. I'm very used to Zig by now.
The line segment always intersects since the line segment lies within the leaf and it is known to be solid.
Okay, so what do we have? We have a node number, which is like a flag or something that, like a tag that contains information if the content is solid or not. So this doesn't exactly work how we have it, because we have like line segments that are either, you know, solid or maybe not solid. This has more like regions that are solid or not. So that doesn't really work exactly how we're doing it. But let's just see here. So, and then you have like vector, then you have like a 2 points. You have starting point, end point. So I'm guessing it's this and this. Both ends of the line, or this arrow here. And then we have intersection, which okay, here it says, yeah, okay, so here it actually says node being traced negative for leaf nodes. Okay, start of the line being traced must lie within the node, end of the line being traced must lie within the node. Okay, what if they don't though? Intersection, the first point on the line segment that is in a solid, not set if the line lies entirely in empty space. Okay.
Since P1 is in the leaf, the nearest point of intersection to P1 is P1 itself. For empty leaves, there is never an intersection since the line segment lies entirely within the leaf.
Okay, so this is only for the case where the line is entirely within this region,
which we know to be empty.
Which makes sense.
If we're in an internal node,
I guess for us, yeah, as I said, we don't really have this thing. It's like because you're never entirely in. Like, why would you ray trace starting from within a solid, ending in a solid? That doesn't even make sense. because you're never in a solid to begin with. So if you're shooting from out here or trying to move in here, you're always moving from outside to the in. You never have the case where you start and end in the solid. Unless I'm missing something. From what I remember, you pick a random segment and choose front versus back, then a random segment, see if it's part or front. Well, it's a binary tree, so as I understand, you start with the root node, and then you try to find your way through the tree, right? Or are you talking about how to build it? How a map is made from that and extruding. Well, yeah, so that's also the thing, like there's different use cases. The thing that I'm doing right now is I can bring up the GIMP here again. I am doing this. So we have this is the level. So we start out with a level. And these are, this is how Doom editor works. So this is like all the line segments. These are all the line segments, and they have 2 points like start and end, a direction, and that's it. So this has 8 segments in total. That's the whole map construction, like structure. And then we build this split algorithm. So let's say we start with this one. I showed it before. So now we split the whole map in 2. So this is the back side and this is the front side. And then we continue here. Let's do the back side. We pick this one. Okay. It doesn't actually, nothing is ever gonna split here because of the way the level is built here and the way and that we choose this one to start with. But basically the whole map is always split into 2. So at this point, this is the front side of this node, and this is the back side of this node. And then you continue, this is the front of this node, this is the back of this node. This is how I've done the building of the tree right now. Okay? And what I'm trying to figure out is like, okay, well, what if you're standing here and you want to move to this point, let's say, how do we use the BSP tree to find out if we're colliding with something in an optimized way without having to look at all the lines, That's what I'm trying to figure out. Off-topic question, do you have any idea to make a 3D pendulum with variable length of string? No, I'm gonna say. Right now. Okay. I'm just gonna continue looking here. Let's see.
There are 2 easy cases to be solid. Since P,
okay.
There is never an
So let's understand, this function was only for start and end in the same region or the same. So what this would be representing is like, I don't know. I don't actually know. It feels like this is fundamentally something else that we're looking at.
Since the line segment lies entirely within the leaf, which we know.
Because we don't have any information about regions like this. We only have lines or planes. And you can see, if we're in front of or behind a line or a plane. But you can't understand if you're inside a rectangle like this. What if there were more? Well, okay. I guess if it's empty, it means that it has no children, maybe. It has no children and it's empty. And solid means it has no children and it's solid, I guess. Maybe that's why we know that, okay, we don't have anything else to compared to. I guess that's why this works.
If we're in an internal node,
Okay.
there are two easy cases we can handle first.
So here's the third
If both the
thing.
start and end points are on either side of the split, then we can defer to the node that they both lie in. Finally, if the start point lies in a different child to the end point
Wait,
he leaves, there is never an intersection since the line segment lies entirely within a leaf, which we know to be empty. If we're in an internal node, there are two easy cases we can handle first. If both the start and end points are on either side of the split, then we can defer to the node that they both lie in. Finally, if the start point lies...
okay, so let's look at that case then. So setup variable later used, node equals to node num. Okay, I see. So either it's like the node num is like, either it's a leaf, which means it's one of these. Okay, and then it's like either it's like a information here which says either solid or empty, or it's like an ID or an index into the nodes array. So here we've got this node, which now we know has children. So yeah, so and then we have a plane which we can get here as well. So that is what we need to check for intersection against. And then we're doing some calculation to understand what is the relationship between our ray and the plane. And it says handle cases where the line segment lies entirely within a single child. So how do we know that? Is it because this is the plane? So we know that we're on both ends are on the same side. Oh. And then we also have these checks here, which I don't think they explain.
Then we can defer to the node that they both lie in.
Or, well, maybe they do, but I don't understand. T1 more than or equal to 0, T2 more than 0. Okay. I'm not exactly... well, these are the dot products. Okay. Well, it's just... I think it's just checking which side we're on. So either we're on... oh, so this is just taking... okay, if we're on the back side or on the front side. I see. So if both of them are on the back side, we're choosing the first child here, or maybe it's the front, whatever. If they're on the other side, we're choosing the other child. I see. Okay, yeah, that makes sense.
Finally,
and then we try, and now, what the hell are we doing here?
if the start point lies in a different child to the end point, we step through the near child first, followed by the far child if necessary.
Okay.
This code finds the point that the line intersects the split plane.
Mm-hmm.
With this midpoint, we can break the original line in two, one half in the first child node and the other in the second child node. We then recursively call the trace function, passing the child node that the start point lies in, along with the corresponding line segment. If we hit something, there is nothing more to do. Otherwise,
Right, so we check the start of the line first. And if we don't hit anything here, we continue to check if we hit something here. I see.
we continue the trace on the far side. In this example,
Okay,
we trace
okay, so it makes more sense. I just need to sleep on this a little bit, I think. Because it's like, when you're looking at this, you have these regions and stuff. I had to kind of, understand how it's all connected and how we actually do all these things. Okay. So actually, if we go back to the GIMP, can we mark this? So, okay, let's go back. So here's the first split. This is, it's, I guess you can say it's not solid or whatever. This, yeah, it's not a leaf, so it's not solid or not or whatever. So, and then we continue here. Now this is a leaf, and it's not solid. well, it's empty, as they say. And this is another leaf here, which is empty. And there we go, now we have 2 leaves. So here's the leaf, this is empty, but this one is solid. Oh, ding, ding, ding. The lights just went up here. Okay. Is my link visible? I don't think links are, they like links for some reason here. Okay. Okay. I think I understand actually. Now let's just try to keep this idea in my head while I try to actually implement this. Because I think we're missing some stuff here. When we build a BSP, the node does not have information. Well, we can kind of check. I mean, we could make a leaf thing here. A leaf, which is either empty or solid. Or no, actually, no, wait. We make a union enum here, and either we have a leaf, or we could just say it's empty or solid straight away, or we have a node or a branch, I guess. We can also call it, which is this struct here. Okay, and now these could be like, instead of being null, let's remove this. They have to be like empty or solid. So let's just initialize them with empty then. And just for convenience, I'm gonna have like a branch instead here. So you will be a branch. Okay. Oh yeah, it needs to be. Oh, wait. No, this. There we go. Yeah. So we need to do this a little bit differently. Okay. Okay, we need to fix some stuff now. But yeah, I think this structure here makes more sense now. So front or back, like if we have a branch, we should have both front and back nodes. Each node can either be empty, solid, or it's a branch, which has even more children. I mean, yeah, this is kind of like it's a branch, it's a split, whatever you want to call it. It's a binary tree. So now we can actually have that information in here. So let's see, let's just adapt the thing that we have here. So the branch, yeah, the node is no longer a pointer. So let's get rid of that. And the root is not a pointer. It is, let's just define it as empty, I guess, for now. And I mean, we don't even know if this is gonna be a split, I guess. It depends. Like, we could have no input segments. So we don't even populate this for now. Okay. Let's start here. So we have the node. We split the space of the node. We have the, but the thing is, like, if we don't have any input segments, okay, then we just return. That checks out. If we're in here, we should have at least one. So now we actually do need to populate the node. So we do need the allocator here. And we're gonna set you to be a branch. And the branch, we need to create a branch. And I guess we could do this to make it easier, maybe. Branch. What else is happening? And then we have, okay, you need allocator. What? Oh. No, okay, yeah, this needs to be a pointer, right? Okay, yeah, fine. It's a pointer there. And so here we provide the address instead. There we go. Oh, there we go. Right, because it's already a pointer there. Okay. You, no field name, segment ID. Union. Maybe we do need the whole node as a pointer. I'm not sure actually. Okay. Node.branch. And now you're not optional anymore. And you need to be a pointer. And I don't think we need to create this because it's gonna get created in here. So actually, we just give it this and it's gonna do it. It's gonna pass it in here and that's gonna split it if it needs to be split. Now the only thing is, like, how do we determine if it's gonna be solid or not? That is the question. Okay, this is actually more simple now. Okay. Wait, it doesn't need to be a pointer. If node is equal to branch or not equal to branch, we return Yeah, cool. Because now we don't need to modify it, so we don't need this. I mean, this code, it doesn't work anyway, so yeah, let's just get rid of this. Okay. Now, okay. So I think we've got something here. The only thing I think we're missing now is how do we determine if a node leaf is empty or solid? That is the question. So if we go back to the drawing here, now I guess what we could do is we could check, does the whole plane contain, well, or okay, my idea was that we're gonna check, like, okay, does this contain the whole line? Is the line the same as the split? Is the split the same as the line? As the wall? Is the split the same as the wall? If it is, then the backside should be solid. Something like that. I don't know. Maybe that doesn't really work. What if you had like a split here and you have two walls, for example? They're a split. How do we know that this should be? Because when we go back here, it's like we split this and this, but they should. Yeah, well, both of those are. But let's say this was empty. How do we know that this is empty or solid? I don't know. Is it always solid if it's on the back? and there's no, and it's a leaf. And on the front it's always empty. Because then we don't actually even need that information, if that's the case. Because you won't have like lines in here. That doesn't make sense. I guess we can try that. So basically, let's assign the backside here. The front side is going to be empty. The back side is solid. And if it's a leaf, it's just solid, I guess. Well, if we run this, nothing's gonna change, I guess, if we did it correctly. It's still, everything's still the same, so it still works the same. But what we're gonna try to do is make like a ray trace from our player position and try to see somehow that we get the correct collision here. Okay. So all right, I'll just BRB 1 second. I'll be right back. 1 minute. All right, I'm back. Oh, penguin. What's up? All right, so what do we need to do here? So this is the entry point idea. it's like, it's saying like colliding segment. What we really want to get, well, because the idea was that if we get the segment, we could get like, I mean, really what we want to do is we want to try, if we want to collide with the player, right? We want to have more information than just the point of intersection. We want to have like maybe the angle, so that we can calculate, you know, that the player can kind of glide against the wall, you know. That's the idea. So that's why I wanted to get the segment so that we could calculate that. But maybe we just need to return a couple of, like, you know, variables to be able to calculate the necessary things. But let's see. So we have start and end. So this is kind of like casting array here. We have a start and end, and we have the start node. Now I'm not sure, like if we look at the example they have here, they have like an intersection that I'm not too sure what this is. The first point on the line, segment P1, P2, that is in a solid, not set if the line lies entirely in empty space. Oh, that's the output. Oh, so this is kind of weird because it's not like marked here. I'm not sure what language this is. Q Boolean. Is this some kind of weird Quake script or something? I don't know, because this would be, unless there's like pointers in this vector here, which I don't think is the case, but yeah. Yeah, okay, so this is the intersection point that we get out. Don't we need more information though? Returns true if we hit, otherwise not, right?
The function takes a node number and a line segment that lies within the node. The function returns a boolean saying whether the line segment intersects the solid. If so, the first point of intersection is also returned.
The first point. I mean, I would guess we want to have some kind of information about the wall that we're hitting.
The line segment is defined as a start point, P1.
I guess we could start
P2.
there.
The point of intersection.
Okay. Let's just start there and see what's gonna happen. So instead of having an out variable, what we can do in Zig is we have an optional and well, now this is not a, well, we can get a point. Let's call it intersection, whatever. Okay. And here we're like checking it. So this is the actual like recursive algorithm here. So, okay. So we had a couple of branches here. So here we can say like if the node is empty, right, and we assume actually that the start and end is like in the same node, because that's like how the algorithm works, right? So if it's empty, that means that we don't have, right, okay. that means we don't have any collision. If it's solid, we should just, I guess we just take the start point. I'm not sure how they do it, if they pick the middle.
And it's the nearest point to P1 that is both on the line segment and in a solid. The line segment always intersects, since the line segment lies within the leaf.
Yeah, I think they take the start. Yeah, the start is P1. Yeah. Okay. Okay. And then we know that it's a branch down here. So now they're doing some calculations with dot products, which I actually am a little bit familiar with. Yeah, they grab the node and the plane. We already have that, I think. And then, well, the plane, I guess the plane normal. I guess the normal is just like a relative vector from that. It's like a direction. I think. And then we have the distance. Okay. So we actually don't have the normal. We could like store the normal. I mean, we have the actual like vector here, but we could store the normal, or we can calculate it. But it's better to store it, because then we don't need to calculate it every time, I guess. Normal. And of course it's 2D, because we're working with a 2D map. Okay, now we need to create that normal. Let's just finish this algorithm first. So let's assume we have the normal. Okay, so normal. So we have T1 and T2. T1 is the dot product of the plane normal and P1, which is the start position. So this would be node branch splitter normal dot to start. So that is T1, and then T2 is end. But then they also subtract. Wait, no, it's like scalar. Okay, they subtract the distance. Oh, so we need to store distance. We need to store the length as well. Okay. I think that was it, yeah. Okay. And let us calculate this now. Wait. This is the only place where we assign it. So we can, here we can calculate the rest of this stuff. So normal. That would be like the direction, I guess, of the thing. So it would be like... So the idea is that we take the start position and go to the end position. We have then imagine around the start position, we imagine a clockwise direction, where the start position is the origin. So imagine a circle, go around the start position. And then the direction would be the clockwise direction where that circle like intersects. The tangent, I guess, where that circle intersects with this line. Maybe that's way too complicated. Explain. How much is in your Zig cache? Well, I actually clear it now and then because it increases. Was it like NT? No. What was that program? ND NS. What was it? There was, I had like a program that you could check. One second here. Sorry about that. Hello, Mimita Simas. What's up? What was that program? There was like a program that you could check files or directory size. What's it? ND U. No. DU. You can easily DU. I think it's only 3 megs right now, but it's like it's always increasing. They never clear it. Every time you compile, it creates a new cache, which is good in a way, but it's also bad because at some point things stop working and you have to deal with it. Okay, so the normal, what would the normal be? It's like we have the vector, and we need to take the vector, which is like the relative kind of vector form of the splitter here, and we need to turn it into the orthogonal or the perpendicular direction. It's just that you have 2 different directions to choose from. Wait, do you actually? There's another cache in TMP. Yeah, there's a global cache as well. I'm not sure. Okay, how do we calculate this? I mean, isn't it just rotating the vector? By -90 degrees. And then normalize. Isn't that just what you do? I think so. Okay. I am from Sweden. Okay. Now, what they do is they check. Let's just get rid of this shit over here. Then they check, okay, well, if T1 is more than or equal to 0 and T2 is more than or equal to 0, we return check intersection we check the, is it the front or the back? So let's think about this. We take the dot product of the normal against the start position. What does that tell us? The normal tells us which direction the wall is facing. So if the dot product is positive, it means it goes in the same direction. Right, it's like which side of the wall is it on? This should be on the front. If it's positive, it should be on the front. I'm pretty sure. So this should be the front. Yeah. Okay, we got Canada. Nice. I don't think I've had Canada, but this is usually not the time when I stream, I don't think. Well, actually it is. Except I usually stream on like weekdays. Okay, and then we check like if they both are. So if they both are on the same side, we're gonna pick that side. Okay, and then so that's that.
Either side of the split, then we can defer to the node that they both lie in. Finally, if the start point lies in a different child to the endpoint.
Right. So here it's gonna check. Okay, here we're calculating at which fraction we are intersecting at, and then we're doing some calculation here. What's this loop here?
We step through the near child first.
What the hell? So the fraction, this is like the actual fraction. Wait, what is this? I guess it's the actual fraction. Wait, no, it's using like T1 and T2. Right, so that would be like where on the thing it collides. I don't know what's going on here. Mid I. Where's mid? Define that.
Then we can defer to the node that they both lie in. Finally, if
Mid is not defined. Wait, is it because it's a weird language? Is this a pseudo language? What language is this? PHP? Okay, so no, because then it would be a bunch of dollar signs everywhere. Because it looks like some kind of C thing here, but then maybe it's not. Maybe it's just not like copy pasted or something. I don't know. But what is going on here?
If the start point lies in a different child to the endpoint, we step through the near child first, followed by the far child if necessary. This code finds the point that the line intersects the split plane. With this midpoint, we can break the original line in two, one half in the first child node and the other in the second child node.
Okay, so I think mid is like this point, and I is simply the vector part. So it's like I is okay. This is just the dimensions. Okay. So it's like, you know, x, y, z, because it's 3. So all it's doing here is taking the midpoint is equal to start of the same, and then it's taking the fraction times the difference. So it's just finding, okay, it's just finding that. I see. You can also take the vector, no, yeah, the difference, scale it. Couldn't you just take the difference, scale it by the fraction, and then add that to the start? Yeah, I guess that's what they're doing here anyway, in a different way. Side gives the child containing P1. Okay, so we're saying like, which side do we start on? Do we start on the front or we start on the back? And then we trace through the children here. That's this, which side it is. So if we start, we start at where the starting point is, and then if that is false, we continue and check the end as well. Okay, I think I got it. And then it all disappears. Welcome back, Penguin. So let's find a ratio, and that was like T1 or was it T2 or T1? T1 over, oops, T1 or wait, isn't it like this? Yeah. So the T1 over the difference. No, it's the other way around. It's T1 minus T2. This doesn't really. I don't really understand this part, but whatever. I don't care really right now. I just want to see if this works here. Okay, so that's the fraction, and then so now we can say that the midpoint is going to be the start position, and then we add the difference. So difference would be end position, subtract the start, and we take difference and we scale that by the ratio. That's what we're doing here. And then we say, okay, which side do we start at? So it's like if T1 is more than or equal to 0, then we should start at the front, otherwise start at the back. This is kind of interesting because they're using numbers for this. I can't really calculate it in the same way unless I'm using like enum to int, which I could do. But let's just type it out here instead. So basically it's just like if T1 is more than or equal to 0, that means we should be at the front. So we have we could also do this. Start side is equal to if T1 is more than 0, the start side should be node branch front, I think. Yeah, because then we start at the front, yes. Otherwise, we start at the back. And the end side should be, you know, if start side is equal to front. Wait. No. We do this again. So if this is you can make this into one branch if you want to use tuples, but whatever. Then this should be back, otherwise this should be front. Actually, you could also use T2 and do the same thing, actually. Whatever. They should be different. These results should be different. Anyway, and then here we're saying if check intersection. So first we start at start position, we end at the midpoint, and then we take the start side. If this is true, we get the result and return the result. Otherwise, we return check intersections midpoint to the end position and use the end side. Yeah, me too, Mutasimos. Alright, see you later, said who. Thanks for stopping by. Okay, so I think that we could have our little ray intersection function working here. So let's test this out. Let's go to main. And let's do like a... Let's do like a thing here. Wants to... Let's do like a shooting. And we're gonna do if mouse down is being pressed. Isn't there like an edge detection? There we go, pressed. And then it's like the left button. See how easy it is? Then we're gonna say shooting is... Well, actually we'll just say shooting is equal to this. There we go. Okay. And then we're gonna go here and we're gonna say if we're shooting, we are going to get... we're going to say if collision get intersection point. Starting point is going to be like camera position or camera position. The end would be camera position plus the direction. But we probably want to scale it a little bit, because otherwise it's just gonna check like a little bit ahead. So let's scale this by, I don't know, that, like, I don't know, 100,000. Okay. You also become a transpiler. Yeah. But I guess. I don't know. What do you mean? Start node is the root node. So I think. Or it's this one. Yeah, it's the one that we calculated from here, I think. Okay, when I see this now, it's kind of coming together now. Actually, it's starting to come together, because we're in a node, so we're in the starting node. Okay, yeah, and so we get the intersection point here. If we have an intersection point, I mean, we could just log it out. We could also make a little cube as well that we want to render. So let's just make hit cube. It's not a constant. Let's just make it into a cube. I think we should have a cube somewhere. Do we have a cube? Yeah. Okay, we have a little cube. Actually, let's make it null. And then when we draw, we will draw the cube over here. So if we have a hit cube, we want to draw that cube. We get the cube and we draw it. There we go. Okay. And here, if we get the intersection point, we now want to populate the hit cube. Do we have an init function? No. Position will be intersection point. Oh yeah, I see a problem here actually. I see a problem. We're gonna have some compiler issues at some point. Size is, let's do like 1 by 1 by 1. Color, yeah, red is fine. Okay, I think we're gonna get some compilers. Yeah, wait. But that was not the one that I was thinking about. But that's also true there. And you are a variable. There we go. You are... Oh. This is the thing, like, if we change this to not be a pointer, we probably gonna lose some synchronization stuff. So I'm gonna keep it as a pointer and we'll just do that. There we go. Here's the issue that I was thinking about. Because we are actually working with vector 2s. And not vector 3s. So really we should actually get well, these are vector 3s. No, let's do a vector 2. And if we don't get one, we return null. Okay, so we got the intersection point. Now is the question, like, where will this point be on the y scale? I mean, I guess it will be... maybe we could calculate it, or maybe we just pick the start or something. I'll just pick the start one for now. So it's just gonna be, this will be x, y will be start, and z will be intersection point z, or actually x, because it's, or I mean y. It's a bit confusing here because we're kind of mixing and matching this a little bit, but it's like in Doom when it's actually just a 2D vector, like it's a 2D map. When you shoot something, it's like there's no z vector, but when they want, yeah, there's no third dimension. So when they wanna, but when you wanna render it, like when you shoot something that is like up at, or you like aim upwards and shoot and hit the wall, it should hit the wall at some point along, like where you're aiming, right? But yeah, let's just do this for now and we'll see. Okay, so we fixed all the compiler errors. Let us see. The reason why it takes so long when we start is because the map is random and then the BSP is calculated and it takes a little bit. So let us try this now. How much do you want to bet that this works? So let me press the mouse button. Yeah. Great. As expected. Oh, and we gotta panic. Access of union branch, field branch. While field branch is active. What? Great. Can you please exit? This is. Is it here? No. So it's okay. There might be some weird corruption going on. Maybe it has something to do with the nodes not being pointers. Because yeah, that is probably it. So we have to change that. Like when we build this. Yeah, because the root node needs to be a... Yeah, okay. Fine. Or actually, well, maybe not. No, let's just do let's just do it like this. But then we can't set it. But then we just set it on the fine. The question is, how do we set this one? No, that's up. Or I mean these ones. But maybe these don't need to be that. So maybe it's just this one. It's kind of weird how it actually did work, though. It works when we just move around. What should I add to my voxel engine? Because you had collision, right? What about? I mean, do you have destruct? Can you destruct the voxels and create new ones on the fly? Yeah, see? It's like we can move around. But it's like when we wanna. I'm pressing. I'm trying to shoot here. Yes. Okay, cool. So how is the world generated? Is it generated? Is it like a static, or I mean a predetermined, or do you generate it somehow? Okay, that was strange. Why did we get... Okay. It failed again, and with the same error. Access of union field branch while field branch is active. I mean, that shouldn't be an error, but I think it's like corrupted somehow. I think the issue is that when we initialize the BSP, when we call build here, no, it should be fine, because the root is not, it's not a... We return this, it should have the pointer in it. If it's not a pointer, it's just a copyable, it's a copyable thing. So this shouldn't be any issues. The only issues that I can see is like copying the arena. But the arena should be copyable as well. It's like something is very strange when we try to do the collision thing. Maybe the branch is not populated correctly. Oops. Wait. This should be back. Okay, I'm not sure how the error arose from that, but maybe it didn't. Maybe that's a different issue. Yeah, it's a different issue. Okay, we still have the error here. Pearly noise with a seed. Okay. Like, I don't know, I'm trying to think about what I would like to add to a word like that, but do you have any ideas of how would you like the world to be? Or what you would like to have in the engine? The message are coming slowly. No, that's because the YouTube chat thing is very slow. So it's like I'm like every message on YouTube is like I'm reading it like long after you actually sent it because of how bad. There's like a long lag between, or it's rather maybe it's the other way around. It's like when you hear me speak, I said that like a minute before or something like that. There's like a lag behind when you actually hear me speaking what I said. Like I read your message and then I say it or speak about it. Sometimes I don't. I mean, I don't look at the chat 100% of the time, so I don't see. Sometimes I don't see the messages like instantly, you know, and answer them instantly. Sometimes I see a message and it takes, but I'm in the middle of speaking with something else or something, and it takes some time before I can actually say, like, answer that specific message. But there definitely is like lag in the chat as well. Yeah, because I've noticed that. I mean, compared to Twitch, where there's no lag, basically. Yeah, intentional by YouTube. Yeah, probably. I'm not sure why though, but yeah. Oh yeah, one thing would be cool with the voxel engine. If you could make marching, or are you interested in that? Like making marching cubes or whatever it's called, that you have like several different arrangements of, like you have, you know, you have maybe you divide the cubes into 8 sub-cubes, and depending on which cube is you know, populated, you have different models rendered or something like that. How do I learn DSA and Algo? I'm not habituated of lead coding interview. They will ask this. What is DSA? What algorithm are you talking about? So, okay, the thing is, like, we check here. If the length is 0, we do this. Really, we could change this. We can move it into here, because I feel like that this is where we're concerned with this more. So it's like, if it's 0, we simply return 2 empty. I mean, yeah, we can just return 2 empty lists here for front and back. But otherwise, we are populating this with a branch and then doing stuff with that. Otherwise, we don't actually do anything with the node. And if we get here and we don't have the segments, this is not going to do anything. It's just going to turn empty lists. These are empty, so nothing really happens. And the node is just, it didn't actually change. And the root node at the start is just a empty node. So that seems correct. But it doesn't solve the issue. Okay, now I got some build errors. Oh, sorry. Return. Okay, it's fairly consistent, which is good because then we can quicker make sure that there's no weird issues going on. Data structure and algorithms was to ask in interview. Okay. I mean, just okay. Data structures and algorithms. I mean, it depends on where you wanna work, I guess. I mean, for example, like I have worked. I mean, I only have professional experience in the web development. And in web development, there's really no... Well, in my experience, when I've worked with it, you know, there's really not much optimization that's being done in web development. So it's like data structures are really not that, like, interesting there. It's more like... But the only, like, data structures that I have learned basically is like the binary. Well, one data structures that are really useful is like binary trees. What the hell is it called? Binary search tree. That is actually kind of. I mean, pretty. It's sort of like a simple algorithm, and it's very useful for not only for building programs, but also, you know, you are optimizing searching for things. One thing, for example, is when you want to search for, you know, you probably use it as well, like in everyday life. Like if you want to search for, oh man, if I can say an example, like in Git, for example, if you want to search for where a bug was introduced and you have a relative flat history, if you're using rebase a lot, you would have a flat history. So you could look at, first you start at the middle of the list and see, okay, is the bug there? If it's not, then you continue searching backwards. Then you take the half of the list that you had and take the midpoint of that. So you're at like 1/4 in, and look at that. So that way, you've reduced the problem very, very quickly, instead of checking, you know, every commit along the way. So that is one thing, very useful data structure that you could learn. Binary search trees. And then, you know, you have the usual, you know, arrays, hash maps, linked lists, doubly linked lists, singly linked lists, things like that. Are you listening to me, code guy? So, there you go. You have a little bit to bite on there. Just go and learn those, and that's probably good enough. Again, it depends on what you want, what you're searching for. Trust me, code guy, if I could do that, I would. Because, you know, I've tasted the fruit of like working for myself and not for anyone else, and I would really love to do that, but I have to pay my bills. Yeah, there you go. There you go. There's your data, structure stuff. Full stack dev role. Yeah, so that's way more than you need for a full stack. Yeah. All right. Yes, I mean, I'm sitting here trying to figure out why this is crashing here, and I don't. Yeah, I'm having troubles here. So sometimes, programming is just tedious analysis of what is going wrong. Did this compile or what? Yeah, this compile, I'm pretty sure. Yeah, and then it crashed when I tried to kind of use the collision algorithm. It crashes for some reason. I don't know why. But it feels like the BSP should be correct because we're already using the BSP. It's just when we try to do this that it doesn't actually work. This is where I create the branch. Wait. No, we should use the arena. I don't think that's the issue, but yeah, we don't actually need to pass the allocator. I just remembered because we're using an arena. Yeah. No, we need an allocator here, but not here. Yeah, you don't need an allocator. Yeah. Okay. And you don't need an allocator. Yeah. Because this is... No, it's this. Yeah. There we go. I don't... It could be that we were overriding something or other, but I don't think so, but you never know. I don't care to analyze what went wrong there. Okay, that was it, apparently. Particles. Did you hear my request, Mutasimus, on the marching blocks? No, still same issue. Or marching cubes. Sorry. God damn it. What if we just try to like we try to print the whole thing out once it's done? It should also crash at that point because it's trying to access all the different points. No? Okay, that just works. Unless it skips here. Okay, let's do a recursive check here then. Let's do like a function. Let's do a format function. Switch on self, and if we're empty or solid, we will get the tag and we will print that. Actually, no, we'll just print self. Otherwise, we get a branch and we can do a format of the branch as well. There we go. And now we go to the branch and we do a format here. And we'll say branch. We'll do like segment ID. We'll do let's do this, and then front, back, and that's it. So segment ID, front, back. Okay, so now we got a recursive formatting going on here, and now we can just use the format specification here to print it out. Of course, we got some error somewhere. Expected dot or okay, there's some issue with this. Probably over here. Oh, okay, right, because yeah, since Zig is just using curly braces here, you have to, if you want to escape them, you have to like double them like this. So there we go. It should go through the whole thing and break. Yeah. Switch on corrupt value. So here we go. So we get the root here, it's a branch. We have the front is a branch. Front. Wow, it goes deep. Oh yeah, because there is actually a lot of these. And so deep in here, at some point, we have a front which panics on a corrupt value for some reason. Okay. Code Guy, it's like to make something more complex, you learn like little bits here and there and learn how to kind of put it together. It's actually nothing more than that. It just takes a lot of time to learn how to do it. Okay. Okay, so it's gonna crash. Maybe we will also speed this up a little bit. Instead of finding the best seed, we'll just pick. We'll just use a random seed here, or just 0. And we get this corrupt immediately instead. So good. We should probably also, because the cubes are random, so maybe sometimes we don't get this. So we have to try a bunch of times to get this. But it seems to be pretty consistent. Actually, no, we should be super consistent. You know what? Let's put a seed. Let's put seed in here actually as well. Because then that seems good. All right, we got our seed. We got the thing there. Yeah. So there we go. There's our random. And now we can do this instead. So now we should get always the same map. Oh. Okay, let's call it R&D or something instead. And now you need a seed here, so let's just pick seed 0. Alright. Now we should always get the same seed, so if we run now and it is a corrupt, good. So we should always get the same result now, so that's good. So we can check if it's actually fixed or not, reliably here. I don't know what you're talking about, cold guy. But yeah, if you want to get good or better, everyone can always get better. You just practice and learn stuff. There's no secret, and there's nothing. Personally, I don't believe in such things as talent or anything like that. I just think that if you're interested in something, if you feel like it's interesting, you will just learn it because that's just natural. You're just drawn to it. And yeah, just take care of yourself, because a good foundation, you will succeed more. And and yeah, then it's just gonna happen on itself almost, because you're interested in it. But sometimes of course it's a job, and you have to put some effort into it as well. If you have it as a job, not everything is of course gonna be fun. Not everything is fun if it's a hobby anyway either. So but it's rewarding. It's also, you have to look at the rewards when you actually get something to work. That is like the most rewarding thing. Like if you, and then you can look back at, yeah, I actually made this and it's actually kind of cool. That is like a really nice feeling. Especially in the beginning, when that you get the feeling the strongest then. Like some kind of, I don't know what it is, some kind of dopamine or something kick out of it when something works. Okay, so we got the basic thing in here, so we can see if it works in the end. So let's see what is happening in here. I'm actually a bit stumped here. Not gonna lie. I feel like it has something to do with this node building here, and we create these branch nodes. I feel like this somewhere here is the issue. It could be unpopulated nodes, perhaps, because it's going quite deep in the tree before it fails. So it could possibly be that. But we are setting these to empty and solid, though. So, okay, let's say that this is 0, for example. But then we'd never actually go in here and set front to something. However, it should be like everything is initialized to empty. I guess this could be initialized as solid, actually. Now that I think about it. Okay. But that does not explain everything here. The longer you are in the void, the more storage the Mindplace 3D logs take up. Like, are you falling into the void, or are you standing in the same place? Like, how do you determine to generate the void? Shouldn't, I mean, yeah, the void shouldn't generate anything, right? Are you falling? Okay. And like, if you determine that the void is just a Y-level boundary, you could say that, okay, well, if you're below this, if the generated chunk or whatever is below this Y, it's just, you just skip that. Is that possible? Oh. Because the velocity is more, so it writes warnings in the logs. The warnings are written both in the client and the server, so 2 times. Oh, I see. Is that why? I was thinking it was like generating space or something. Okay. So you could put like a maximum velocity or something. This is strange. I don't understand what is going on here. Maybe it's this. No, that should be fine. This should be a stable pointer here, and then we just give a pointer into that. So that should be fine. Front and back. I mean, we could say if node is a branch, we then populate these two. If it's not a branch, we don't actually populate them. And we don't even do this because I just feel like that should be how it is anyway, but okay. Maybe it's like no. Oh, wait. We never actually. Okay, I think I know what's going on. So we create the branch here, but this is done in like an undefined value. It's like it doesn't, it doesn't initialize this to anything. So we got like random values in the branch. So okay. So we need to like initialize it. Did we have an init function here? No. So we just initialize it. I think that's just what we need to do. And I guess here, like if it's not a branch, we return. Hello, Samath. Welcome. Okay, there we go. Okay, so we got rid of the crash. But the problem now is that the intersection algorithm does not work. Okay. Like, I don't see any cubes anywhere. If we click here and we go on the back... Oh! Wait, is it just that the thing is... Wait. Oh! Wait, it does change. It's just... is it just that it's below? What the hell? Permanently destroyed my testing while trying to test flying. Wow. What is bang type in SIG? It's an error union, yeah. But what does that mean? It means no. It doesn't mean any error. It means it just means that the error is inferred by the usage. So this is actually, if you look at the type, okay, well, it doesn't say here, but it actually does have a specific error. It's just that it's inherited by whatever the error we get from in here. I think for this case, it is simply an allocator error. So yeah. Usually it's like a code smell sometimes to not type out the error because it's more clear what can go wrong if you actually have the error here. So usually you wouldn't want to have an error here, but you know, if you're just making a quick thing and you don't really care and no one's gonna use this code anyway, then you know, you can just do this too. You don't really care. But I think it's a good idea to actually always put the error here. But yeah, I need to go now. Sorry about cutting it short here, but yeah, I think we did a really good progress here. I'm probably going to do one more quick stream of this, and then we'll look at something else. But sorry I have to go now. Thank you very much for watching, and I'll see you later. Have a nice day. Bye-bye.